so let's go through those definitions. Again, at the first of this chapter especially, there's a lot of different definitions as to what things mean and how they represent. So let's first talk about linear versus nonlinear. In general, what is linear versus nonlinear? What does linear mean? It creates a line. Okay? It creates a line. That's what linear means. A nonlinear, what?
Just dots.
Doesn't create a line. Well, it may not be dots. It may be curves. It may be dots. It could be dots, but it could also be curves. So nonlinear means it does not create a line. Linear means it creates a line. Those are pretty easy. Now, how do we represent functions? These are some different ways. So let's take a look at these. What's this called? No. The way it's being represented, what is it called? Mapping. Very good. This is mapping. What is this called?
Mapping.
Nope.
No.
This is mapping. This is what? Ordered
Operation.
Pairs.
Ordered pairs. Very good. Mapping, ordered pairs. What's this? Graph. Okay. What's this? It's a graph, right? What's this? An equation. Okay, this is another way it can be represented. Equations, mapping, and
Ordered
set of
pairs.
ordered pairs. Okay, so these are the different ways you can represent anything, and anything can be considered linear or what? Non-linear. And the other thing that we're going to talk about that I want to make sure you know is discrete versus continuous. So discrete means either a beginning and an end. A discrete function has a beginning and an end, or it has exact points not filling in the in between. Exact points not filling in the in between. That's what discrete means. So, and then continuous means what?
Keep on going.
It keeps on going in both directions. Right. Okay? So we're going to talk about all that stuff while we're doing these. A lot of these are kind of repeat from what we did yesterday. Should be a good review for you. Tristan, is the first one just a relation or is it a function? This one right here. Is it a relation or is it a function? And how do you know?
I don't know.
Okay, how am I going to tell if this is a relation or a function? Seth, how am I going to tell? This is from last time. Go ahead, Jacoda.
If it's got more than one.
Yeah, if it has more than one arrow coming out of a x value, then it would not be a function. If it only has one arrow coming out of each x value, then it is a function. Do I care about the number of y values? No. Just because this one has only one y value, it's still a what?
Function.
Function. Okay, so this is a function. How come? For each x,
There's only one.
right, for each x, there is exactly one y value. Okay, so that's how we know it's a function. Is this discrete or is it continuous?
Continue.
Is it just a set of a few points or is it going to go on forever?
Go on forever.
This one's going to go on forever? Does it have the value 3 in the domain?
No.
Does it have the value 0 in the domain? Does it go on forever then?
No.
No. It would have to have all reals in the domain, right? So this one is not continuous. It is what? Discrete. Okay, so I'm going to write discrete. And the way I'm going to put discrete, the way I know it's discrete is that there are a limited number of values in the domain. Okay, that's how I know that it is discrete. Is it linear? Well, we're going to find out. I'm going to show you how you can tell if it's linear. Obviously, it's not linear unless it's what? And this is something you want to write with linear. It would have to be what? If it's going to create a line that continues on, it's got to be what?
Continuous.
Continuous. So this is not linear only because it's what? Discrete. So that's something you might want to put in your notes by linear. A linear function must be what?
Continuous.
Continuous. Write that next to linear. Okay, a linear function must be continuous. Okay, linear function must be continuous. All right, so let's try this next one. Okay, using the ordered pairs. I'm going to draft one more too. There we go. Okay, so let's do this one with the set of ordered pairs. Is it a function or not a function, and how do you know it? Is this one a function or not a function?
Function.
It is a function. How come?
There's only one x each time.
Yeah, there's only one x mentioned each time. So if the x was duplicated, if any x is duplicated when written this way as a set of ordered pairs, it would just be a relation, it wouldn't be a function. But this is a function. Again, for each x, I keep putting an e on 4, I don't know why. For, I guess because I'm trying to write each right after. For each x, there is only one y value. Okay? And that's how I know it's a function. Okay? Is it discrete or continuous? Callie, is this one discrete or continuous? Does it go on forever?
I was gone from this, that last.
That's okay, just pay attention to what we're doing today then. So discrete just means that we have a limited number of values in the domain. Are we limited in how many things are in the domain? Yeah, there's only what? 4 things. There's 2, 3, 4, and -1. So if it's limited, it is what? It's discrete. And again, that's kind of a new word. I think I just called it non-continuous last time. But discrete is what we're going to be calling it. So discrete because there's a limited number of values. So could this possibly be linear then? No. Nothing that is discrete can be what? Linear. So I'm going to say this is non-linear because it is discrete. Okay? And that's the reasoning there. All right. Let's go to the next one. We have a graph. On a graph, how are you going to tell if it's a function or not?
If it goes in
Yeah, you draw vertical lines straight up and down through the graph. If it hits it no more than once, so like that one didn't hit it at all, right? But these are only hitting it what? Once. And you can draw an unlimited number that you want. Make sure that it never crosses the function, this is the function, more than once, right? It only crosses it once, it must be a what? Function. So I'm going to say function by vertical line test. Only crosses at most. Remember how we used to use that phrase on the greater than, less than? At most. That means it can be 0, but it can't be, and it can be 1, but it can't be more than that. At most 1 time. That's how we knew that one was a function. Okay? Is it discrete? Or is it, what's the other one? Continuous. Is it discrete or continuous? Well, this is kind of a weird one. It's continuous. And I need to put some values on here. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. So if I was to say, hey, it's continuous between -3 and 7. Okay? Meaning that from here to there, it's continuous. But otherwise, it would be what? It would be discrete because it has a beginning and an end. So it's only continuous between -3 and 7. That's the domain, if you will, right? So it's continuous in that domain, but everywhere else outside of the domain, it is obviously discrete. So, because there's nothing there. So it's only continuous between -3 and 7. So this gives us a domain, by the way. Have we talked about domain yet? Okay, let's talk about domain. So you want to put this in your notes also. Domain and range. Okay? The domain is the set of all possible values of x. Write that down in your notes. The domain is the set of all possible values of x. That's why I said it's continuous between -3 and 7. Because from -3 to 7 are my possible values of x. So the domain on this one is x is between, and this is where we use our greater than, less than. X has to be greater than what?
-3.
What does x have to be greater than?
-3.
-3. So you go from the far left, you always read left to right. X is greater than the -3, but it has to be less than what?
7.
Less than the 7. Now because we're hitting those points and we filled it in, we're also going to say equal to. Okay? Does everybody understand domain then? It's the possible values of x. It can go anywhere from -3 over to 7. It can be, x has to be greater than -3 and less than 7. So that is our domain. And we learned that when we were doing the inequalities last chapter. Okay? How about our range? Well, again, we're going to need some y values here, so let me throw those on there. 1, 2, 3, 4, and down 1, 2, 3. So what is our range? Well, the lowest it'll ever be is negative what? 3, and the highest it'll ever be is 4. So range deals with all possible what values?
Y's.
Y values. So x values are the domain, y values are the what? Range. Put that in your notes. The domain is the set of all possible x values. The range is all possible y values. So the range in this case would go between -3, and again I'm comparing the y-axis here to 4. And that's my range. Okay? So range, you want to look at y values. Domain, you want to look at x values. Okay? It's continuous between there. On the ends after that, it's obviously not continuous. But between that domain, it is continuous, meaning that it's going to hit every little point. Halves, 0.1, 0.2, you with me on that? -0.5. All those have possible values. -2.5 has a possible value. Once I get past -3, though, is there any values? No. So that's why it's continuous only between those values. All right, take a look at this top one up here. Is this a function up here? Danny, why isn't it?
Because it doesn't cross the y.
Yeah, if I drew vertical lines, it would hit it how many times?
Twice.
Twice. Think about that. If I drew a vertical line through there, how many times would it hit that function? Twice. And Danny said it didn't cross the y. That actually is a hint as to when it probably won't be a function. So if it curves back around and doesn't actually cross the y, that's actually true. That's very often not going to be a function, okay? But it's more because we can draw a vertical line through here. I could draw one like this, Danny. Would that be a function? Yes, this is a function. This is not. Because this one, if I drew a vertical line, would hit it twice. So this is just a relation. A relation is just sets of ordered pairs, which this could be turned into. So this is a relation, not a function. Vertical line hits twice. Okay, this would be a function, because even if I drew vertical lines through it, even though it's curved and even though it doesn't cross the y-axis, it's still a function, okay? This one is only continuous from 0 on, right? Because it's not gonna go past the y-axis, so that's what Danny was saying. This would be only continuous for the domain from 0 on. Okay, vertical line test then doesn't fit, pass it. Is it linear then? No, not linear. Non-linear. Doesn't create a line, you could say. Not a line. Okay, things like that. Is it discrete or is it continuous? Is this discrete or continuous? Continuous as long as we're bigger than what? As long as we're bigger than what? 0, right? As long as the domain is above 0. So continuous for x,
Y.
domain x has to be greater than or equal to 0, okay? The range is actually all y's, because as you go further out, you're going to go further up and further down. All right, this one, the equations, these are the most important, and these are the easiest actually to tell, okay? Now, first of all, can I turn a table into a representation of a mapping or a table or a set of ordered pairs? Yeah, I can do that. So, Logan, so let's say I wanted to turn this into a table. I'm going to put in an x value, I'm going to find a y value. Let's pick a few. Let's say we have -2, we have 0, we have 2, we have -1 and 1. Okay? Logan, will you put in -2 for me and tell me what I'm going to get? Good. Did everybody see how he did that? He put in the -2 for the x, and he said, all right, I got -2 times 2, which is -4. And then he said +3. So -4 plus 3 is what? -1. So that's the value when you plug in -2. Everybody with me so far? Okay, how about 0? What would that give me? So I'm going to put in a 0 for x. What's 0 times 2, Gannon? 0 plus 3, 3. So my answer there is 0 is 3. Okay? 2. Briley, put in 2 for me. So put in 2 for the x. 2 times 2 is?
4.
Plus 3 is?
7.
7. Very good. Okay, Griffin, put in -1 for me.
3.
2 times -1 is? Don't add it, by the way. 2 times -1 is?
-2.
-2 plus 3 is?
1.
1. Okay. How about 1, Seth? What will 1 give me? 2 plus 3, which is? 5. Very good. Okay. So there's my representation. Does that include every value? No. I could put in a half. Wouldn't be as easy, but I could put it in. I could put in 100. Because this one is a continuous function. Okay, so usually, almost always, this is key, when you have a representation of a equation, it's almost always going to be what? Continuous, and the domain is going to be all x's. So x is an element of what we call the real numbers, is how we write that. Okay? The x's can be any real number. Can I pick any value of x and get a y value? Yes. The y values sometimes are limited. In this case, the y values are also any number, because as I go further and further negative, what's going to happen to the y's? They'll get negative, 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 negative. They'll get further down. As I get bigger and bigger positive, notice what's happening. It's going to go further and further what? Up. So the range is also, y is an element of the reals. That's not always the case, but it is in this one. Okay. So because of that, we know it's continuous. We know we have our domain and range. Is it linear? Is it linear? There's a couple ways to tell. And this is what I'm going to show. Without graphing it, there's a couple ways to tell. First of all, and you wanna write these in your notes. So here's ways you can tell something is linear. If the x is to the first exponent only, so x to the first, it's not x to the second, it's not x to the third. If x is to the first power, it will be what? Linear. You want to write that in your notes. If x is to the first power, it will be linear. So this one I can tell it's linear because x is to the first power. So if there's no number up above the x as an exponent, that means it's 1. And if it's 1, it's linear. Okay? So this is linear. Here's another way to tell though. Let's write these in order. This little representation. Let's write them in order, starting from the furthest negative. So let's go -2. I'm going to make a table like this. -1, 0, 1, 2. Everybody with me? These are my representations of my x values. Okay? Now let's put the corresponding y values for those. At -2, where were we at?
3.
-2 what?
-1.
-1. -1. Go through real quick and just tell them to me.
1.
1, 0, 3, 1,
5.
5, 2,
7.
7. No 6 on there. Okay. Okay, we're just copying this down to here. Now, here's the important part, and this is kind of tricky, and it's cool, actually. This is kind of cool. So if you're not paying attention, pay attention now. Okay? So Tristan, pay attention here. Logan, pay attention. And everybody pay attention. So this is important, because this is kind of cool, and it's really how you tell things are linear. What's the difference? In other words, how do I get from, I'm saying what's the difference, but really what I'm saying is, how do I get from -1 to 1?
You add.
On a number line. Add what?
2.
2. Everybody agree with that?
Yeah.
You add 2. So I'm saying difference, but I'm meaning how do I go from one to the next? How do I go from 1 to 3?
You add 2.
And how do I go from 3 to 5?
Add 2.
And how do I go from 5 to 7?
Add 2.
So if you use common integers and you have a common first difference, it has to be what? Linear. Okay? So if the first differences are the same value, doesn't matter what that value is, in this case it was 2. Could it be 5? Could it be 7? Could it be negative? Sure, it doesn't matter. Anything that those are always going to be the same, it will be linear. So there's a couple reasons why this is linear. One is because it's to the first power, that's one way to tell. Second, if I had a table of values and their first differences were all the same, okay, then this would be linear. So it's also linear because we have common first difference of y values of 2, okay? So our common differences of the y values is 2. Doesn't matter what it is, by the way, 2, 5, -5, nobody cares. Just that they're common, meaning they're all the same. Okay, let's take a look at this one. Is it a function?
Yeah.
Well, we better find out. Let's try and think about this baby as a table a little bit again. So we're going to make this a little table. I'm going to do my table this way so that I can easily combine it into to determine first differences and such. Plug in values for x, find values for y. This is kind of tricky. Okay? Is there an x in the equation? Nick, is there an x in the equation?
Yes.
Where is it?
In front of the F.
Okay, in front of the f. So on this side, this really represents y. It's saying you're going to plug in values of x over here. On the right side, then, is there an x, Riddick? No, Ryder. Which one is it? Is it Riddick or Ryder? Ryder. Sorry, Riddick sits in that same seat like 2 classes from now. So, all right. So Ryder, is there an x on the right side? No. So when I plug in values of x, is it going to change the value of y? No, because remember, f of x is y. So y is always going to be what? 4. No matter what I pick. Let's pick -2. Is it gonna be 4?
Yeah.
Yeah, because I'm not plugging in -2 anywhere. How about I plug in -1?
4.
Still 4. How about 0?
4.
How about 1?
4.
And I can keep going, right? Now, let's see if this is linear though. Okay? Gannon, how do you go from 4 to 4? How much do you add?
0.
0. 4 to 4, how much do you add, Seth?
0.
4 to 4, how much do you add, Canyon?
0.
Huh. Those are all exactly what?
The same.
The same. Is it linear?
Yeah.
Yes. Okay. So I'm going to say this is continuous. Could I plug in any value of x?
Sure. Yeah.
Sure, it's not going to change anything. The y's will all be the same. So the domain is all reals. Because I can pick any x I want. What's the range on this one though?
Y.
What's the value of y? Always.
4.
Only 4. So y has to equal what? 4. That's the range on that one. How about is it linear? Yes, linear because the common difference is what? Common difference equals 0. So all these are 0 on those common differences. Okay, and we know it's linear. It's continuous, its domain is all reals, the range is 4, it's linear, and the common difference is 0. Okay? All right. Good enough. Oh, is it discrete oh, we just talked about that. It's continuous, so it's not discrete. Okay, let's look at this mapping over here. Now, once you see a mapping, unless it has something like ... at the end, is it ever going to be continuous? No. It'll always be what? Discrete. Why? How come it's discrete? Is it unlimited in the number of things in the domain and range?
Yeah.
It's unlimited?
Oh, no.
Is 18 in the domain?
No.
No. Therefore, if the domain and range are limited, it's discrete. So I'm going to write that. Domain and range are limited. Okay, so that's why we know it's discrete. Is it a function, Callie? Callie, is it a function?
Oh, yes.
How do you know? You're right, it is. How do I know it's a function? There's an arrow coming out of, only one arrow coming out of what? Each x, okay? So therefore, for each x, there is only one what?
Y.
One y value. Okay? Does it matter that the y value of 9 is used twice? No, I only care about the arrows coming out of the x's, not going to the same y. You with me on that? I don't care if the y is used more than once. I just can't use an x more than once. That's key. So this is a function. And the reason is because for each x there's only one y. So it is a function. It's discrete, meaning it doesn't go on forever. Can it be linear then? Can't be linear no matter what if it's discrete, right? Because it's only going to, there's no points in between those. So this is discrete, it's non-linear. Okay? How about this one? Okay, Tristan, is this a function or not?
Which one?
This one. Just that set of ordered pairs. Is it a function or not? Why not, Seth?
Because there's 2
2 negative what?
negative 2.
2 negative 2. So he notices that the x value is used more than what? Once. If the x value, any x value, doesn't matter which one, if any x value is used more than once, it's not a what?
Function.
Not a function. So not a function x of negative 2 maps to both, and that's key, 1 and 4. If it maps to two things, it is not a function. -2 goes to both 1 and -2 also goes to 4. That's not a function. If I was to do a mapping of that with the arrows coming out of it, then -2 would be only mentioned once, but there would be how many arrows coming out of it? 2 arrows coming out of -2. That's why it's not a function. Okay? Is it discrete or is it continuous?
Discrete.
Discrete. There's a limited number of values. That's all there is. So this is discrete. Therefore, it's non-what?
Linear.
Linear. Okay? Pretty easy. How about this one right here? How about this one right here? Is it a function?
Yes.
How come?
Because
I could draw what?
a line up there.
Vertical lines through the graph, and it would hit the graph only what?
One time.
Once. Even if I continued this out, which this arrow says it should, it could continue in that direction. Even if I went clear down here and I drew a vertical line, it would still only hit it once. Okay? So that is definitely a function.
Continuous.
It's definitely continuous because it continues in both directions. Is it linear?
Yeah.
Yes, it obviously graphs like a line. It's linear. Okay? You can see a lot with a graph. I like the graphs the most because they're the easiest to tell, right? You can just kind of look at them and you know whether they're linear. You know if they're continuous because it will continue on. It'll have arrows on the ends. It will, it's a function as long as I could draw vertical lines through it and hit it only once. And I could draw vertical lines anywhere and it would only hit it once. So that one's a function. Continuous, linear. Okay? What's the domain on this one, by the way? What's the domain? What could x be? Could x be 100?
Yeah.
Could x be -100?
Yeah.
Yeah, it could go on forever. So x has to be just an element of the what? Of the real numbers. Any real number. Any number you could pick, it'll work. Okay? How about the range? Will y be a big, huge number? Yeah, if it's in a negative direction, it could be a big, huge number. If it's in a positive direction, can x be any, or y be any negative value? Yeah. So the range is also what? Could y be anything? Yeah. Could it be any real number? Again, that range is sometimes limited, but sometimes not. Like on this one, the range was only what?
0.
4. If you think about it, if I have a, watch, if I have a line right here, say at -2, sorry, that's not a very good -2, but let's say I had a line like that. What's the domain of this? Can x be any real number? Yeah, x can go as far as it wants to the right and left. So the domain is x is an element of the reals. But the range is what? What's the only thing y can be? Negative what? -2. Y doesn't go up or down. So range there is y has to be equal to -2. And that would be the range on that one. Okay? All right, let's try these out of your book. You can stop.